Imagine a spring hanging down with a weight at the bottom. If you pull it out of equilibrium and let it go, the equation for its motion is a simple harmonic that can be expressed as a second-order differential equation. The characteristic equation is m lambda squared plus b lambda plus k equals 0. This can be solved with the quadratic formula if necessary. In cases where imaginary roots are found, we call the system underdamped. The spring weight system will oscillate but will lessen with each period until it reaches equilibrium again. Here is an example system to solve. An 8-pound box stretches the spring 1.6 feet. We can use this fact to calculate the spring constant momentarily. If you pull down on the box and let it go, it will oscillate up and down. Let's solve the equation for the box's motion upon pulling it down 4 inches and letting it go. Here we assume the damping force is equal to the velocity of the mass. The general equation is my double prime plus by prime plus ky equals 0. We need the mass, m. Mass is weight divided by the acceleration of gravity, which is 32 feet per second squared. The mass is 1/4 slug. B is the damping coefficient. It describes how fast the system is damped and is related to physical phenomena such as friction. In this problem, it's equal to 1. K is the spring constant. It describes the stiffness of the spring. It relates the force needed to move a certain distance. It's equal to 8 pounds over 1.6 feet, which equals 5 pounds per feet. Plugging these values into the characteristic equation, we get 1/4 lambda squared plus lambda plus 5 equals 0. This is equivalent to lambda squared plus 4 lambda plus 20 equals 0. This equation must be solved by the quadratic formula. Lambda equals -2 plus or minus 4i. Equations with imaginary roots take on a special form. Y of t equals e to the -2t times the quantity of c1 cosine 4t plus c2 sine 4t. We can calculate y prime with the chain rule. This gives us y prime of t equals e to the -2t times the quantity -4c1 times the sine of 4t plus 4c2 times the cosine of 4t, minus 2e to the -2t times the quantity c1 cosine 4t plus c2 sine 4t. Plugging in 0 for t, we find y of 0 equals c1. We also know that y of 0 equals 4 inches, or 1/3 of a foot. Y prime of 0 equals 4c2 minus 2c1. This must equal 0 because the box has 0 velocity at the exact instant it's let go. Therefore, c2 equals half of c1, or 1/6. Finally, the general solution is y of t equals e to the -2t times the quantity 1/3 cosine 4t plus 1/6 sine 4t.